Hello everyone. This is your host Irfan Nasser, and I have just created this YouTube channel to share my knowledge that about the subject of critical soil mechanics, which is one of the important subjects in the MSc Civil Engineering module, MSc Civil Engineering course that people study in the University of Birmingham. If you are getting admission in the University of Birmingham in the MSc Civil Engineering course, you will have this, module in that, and it will be taught by one of the senior most professors, Dr. Ian Jefferson, professor. He's one of the nicest guys I've ever met, and the concept that he gave is still fresh in my mind, and I kind of like the way he taught us the subject. So, without further ado, these are the notes that have been provided by the university, and I'll be just explaining what I have learned through these notes. I'll be reading this and explaining to you guys in a series of lectures. And I'm intending to also, I will try to solve the questions that have been provided in this tutorial section of every lectures. I have solved every single lecture during my, sorry, I have solved every single question that I have come across during my examination period and had a good practice, and therefore I'll be sharing all the tips and tricks that I have learned regarding this subject. So without further ado, let's start with the critical soil mechanics. This is the lecture, the first section of the notes that you will be studying in the university. It is mostly regarding the history behind the soil mechanics thing and also some of the things that you have already learned in your bachelor examination. But obviously, the theory of critical state soil mechanics was developed at the Cambridge University by two researchers. Their names have been given, and Professor Roscoe uh, is one of the most important figures because in the later stages of the lectures, you will see that we will be using some kind of graphs that have been named on the Professor Roscoe's name. And so what he did was the theory was devised as a unifying model of soil behavior and relied heavily on concepts that were identified by other workers. So now this is some of the history, then these are some of the books that you can go through if you want, but we will just move forward. Now, this is the starting that behavior of soils under shear. So basically, we have studied in our bachelor modules and bachelor courses that soils do tend to undergo a lot of stress, and one of the stress is known as the shear stress. So if a soil is subjected to shear stress in a shear box. Now, shear box is one of the apparatus we use in laboratories in order to test the soil's soil strength and all that. Okay, and I'll be explaining this in the further. Now, the typical shear box test results are plotted in terms of shear stress against the shear strain. Now, anything that we do plot regarding the soil in a shear box test, we have to give the results in shear stress against the shear strain graph. Now, the shear strain in the sample is proportional to the relative moment of the two halves of the box. Now, the box moves like this, like shear. So it is basically related to the relative moment. Now, how these two layers move in that box. And in this example, as you can see, now in this shear box test, the soil sample is basically sliced half, and one of the part moves to the right and the other part moves to the left. So as you can see, this is the normal stress because the no stress has been coming from above, and this is the perpendicular to that normal stress, which is we call as shear stress. So this is the schematic diagram of what happens in a shear box thing. Now let us consider an example in which we are considering that a drained test. Now keep in mind that give me 1 second. So you have to keep in mind that we have a drain test. Now, drain test, what it means that the water is being allowed to drain out of the soil. So let's consider a drain test in which pore water pressure. Now, if there is a drain test, what happens is if you are allowing the water to seep out of soil, there isn't any pressure put forward by the water because obviously water is being drained. So a drain test on a soil at three different densities. Now, what happens? This is basically an example that we're considering a soil in a drain test, obviously, and in a shear box. And if we have three densities means the one of the soil is dense, means it's like compacted, like this. One is loose, like the grains are away from each other, okay, and one is in the medium between that. So under the same normal force. Now this is the normal force that I have already explained in the previous thing. Now this normal force, let me just go and draw something. This normal force has been applied on this, you know, soil sample, and we have three different states. One is the dense state, one is the loose state, and the middle one is the, you can say, intermediate state between these two. So if a normal stress is applied on the soil sample, what will happen? Now we will see. Now you can say that if the soil is dense, if the stress is applied, it will reach a shear maximum over here because it will require a lot of stress to be disintegrated. Because at this time, you can say at the peak stress, after that the strain soil starts to shear, like, and it starts to change its dimension, or you can say strain a bit. But if we talk about loose state of the soil, and if you apply a stress, normal stress on the soil, it will eventually directly go towards the ultimate shear, ultimate shear. Because now, for dense state of the soil to reach the ultimate, it has to first go to the maximum shear stress because the grains are basically uh, you know near to each other, so therefore they do not break easily, obviously. So they have to first go up, and then they have to reach the maximum shear. After that it starts to disintegrate, and it goes towards the ultimate. This is the representation of shear versus you can say strain. Now initial densities are there. Okay, density we already know, mass per unit volume is the standard definition of density. Now this example was basically of a soil which was subjected to initial stress, and the stress was actually you can say same on all these soil members. The stress was same, so therefore uh, you can say different behaviors of the soil at the same normal stress. But if we talk about sample of the soil which has been uh, you know tested under increasing, you can say, normal stress. Now keep in mind that the density is same, all the soils have the same density, but the stress has been increased, obviously. Now for this soil, for the first soil, if the density is same, but we are applying different kind of normal force. So if you can see in this graph, the first soil sample will reach the ultimate strain at a lower point here, okay. But if we are increasing the density, sorry, we are increasing the normal force, you can see that the second sample of the soil reaches here, and after that it starts to disintegrate. The third sample of the soil reaches here in the graph. This means that if you keep on increasing the shear stress, okay, so what will happen is that the soil will reach the ultimate strain at different, you know, shear stresses. In this case, as you can see, what was happening was basically the behavior was changed, because if in case of a loose soil, right, it goes directly to the strain because there isn't any disintegration because it's already loose. So it won't require a lot of shear stress in order to disintegrate it because it's already disintegrated. If we talk about the dense sand, it will require a lot of stress. Now, this is what I wanted to share. And shear maximum increases as normal force increases. So this means that if you are increasing the normal force on that particular soil sample, the shear maximum will keep on increasing. This is what happens in a test. If you're testing the soil sample, this is the behavior of the soil sample. Now, shear stress versus shear strain for a sample of sand at different initial normal stresses, in which the shear normal stress keeps on increasing. If you are increasing it, then shear will increase. Because here it says that considering now three samples of soil is at the same initial density, but increasing normal stress. Okay, so if you are plotting the values of shear maximum against the shear stress. Now, effective stress. There is a concept in soil mechanics which we say effective stress. Basically, effective stress, what does it mean? That if you are removing the pore water pressure from the initial stress, that value is known as the effective stress. Because here you can say the different lines are found depending on the density and not on the stress. Now, you can say shear maximum versus effective stress. If you graph these things here, if you plot it like this way, because now there is no pore water pressure, so there will be the lines will be like this, because there will be dense, then there will be medium, there will be loose soil, and this is the angle. Uh, which is I forgot the name of this thing, but there will be the name here. So maximum shear stress versus the effective stress, where delta dash phi dash L is the phi dash for loose soils. This is the angle basically. I forgot the name. Let me check. And phi d is for the dense soil. So effective angle of inclination, something like that. Well, I'll check in the next thing. So this is basically phi dash L is the angle for loose soil, and phi dash D is the angle for dense soil. So this is if you plot the graph between shear maximum against the effective stress, because effective stress, as I have already mentioned, that is total stress minus the pore water pressure. If you go down here, you can see that if we plot a graph between the ultimate shear stress and we plot a graph against the effective stress, what what we get is we get a uniform line, because we have seen that uh, this thing, where did it go? Ultimately, every point reaches the different. Ultimately, every point basically reaches what? The same, I think so. This is not the case here, because it is saying that, okay, as phi is equal to this one, then this depends on, however, plotting ultimate against the total gives. So this means that this is, it has shown all these densities, because ultimate shear is obviously they are reaching the same point at the end. This is what it wanted to say, because if we it has shown all the densities in one plot, because he has plotted the ultimate shear stress against the effective stress. Therefore, there will be a single uh, line which will show this thing. Now, this is the critical angle at which it starts disintegrating. This is basically the ultimate shear stress versus the effective stress graph. So we have in the last two notes we have studied about, if we're plotting a graph between ultimate uh, you know stress against the uh, you know effective stress, and also we have studied the shear stress against the strain, and we have also studied this thing. Now, see, there is a difference I forgot to mention here. Now, this is basically the shear maximum, and this is the effective normal stress. The previous graphs were about the shear and shear and strain, right? This is basically the normal stress and the shear stress. So these are two different graphs. You need to be careful when you are studying here. Thus, as in figure 4, knowing that tan angle ultimate is equal to tan ultimate. Now, this is the basic formula because we know in here that if we talk about this trigonometry here, this graph basically we have seen the ratios. Tan angle is basically perpendicular divided by base. So perpendicular is T ultimate obviously here, and this stress dash is the base one. Now, if the pore water pressure is zero in the figure 4 here, if we say that the pore water pressure is zero, then what we say, because it is a drain test, right? So therefore, pore water pressure would be zero. This means total stress would be equal to the effective stress. Now, this angle ultimate is independent of density and defines the critical state of soil. Now, this angle basically doesn't depend on the density, and it basically defines the critical state of the soil. Now, it is also explained that there is a single straight line relationship between shear stress and normal effective stress, like this one, for the soil when it has reached its ultimate or critical state. Because there will be a single line, obviously, every soil will shear, right? At the end stage of the soil is basically it disintegrates after a load. So, therefore, it has shown a single straight line between shear stress and normal effective stress for soil when it has reached its ultimate or critical state. Irrespective of the initial stress state of the soil, the ultimate stress state of the soil will lie on the line which is defined. Now, it doesn't depend on the initial stress. It doesn't depend that soil has been, uh, you know, uh, there is a load on the soil or something like that. We don't need. It doesn't matter that if there is initial stress on the soil or not. The ultimate state of the soil will be actually on the line, which will be defined by critical angle like this. And delta dash C is a soil constant. Now, this is basically a soil constant. And for that soil constant, the values are basically 25 degrees for heavy clay. And for well graded, we have 45 degrees. Now, these are basically the values of that particular soil. Now, these values have been taken from experimental testing in the labs. And after that, we have got these values. Now, there is another concept of soil dilation. Now, we have discussed about different soil states in the previous slides. Pardon me. And we have studied about different uh, stress profiles in the previous two, uh, lecture notes. Now, there is another concept of the soil which is called as soil dilation, which is basically a property of soil which distinguishes it from other engineering materials under the pure action of pure shear stress. Now, what happens is this is a property specific to the soil. Now there are other materials of engineering, right? There is a cement, there is a stone, there is different types of material, but this property is only limited to dilation, soil, because the dilation property it is the thing which you know changes, it distinguishes or differentiates soil from other materials. Soil will in general change in volume, yes. Dense soil, dense soils will dilate. The reason of dilation, because what actually happens is that soil sample is like this. If the soil is dense, like it is like a strong bowl shape. Now, if you are applying a lot of stress on that thing, soil, eventually it will reach a peak, as we have already seen here in the previous graphs. It has been mentioned. So if you are keep on applying the stress, eventually there will be a point that after it will start disintegrating, and therefore the strain will continue to increase. So this means that if the soil is dense, it will increase the volume. right? And if we talk about the loose soils, if we have the loose material, soil material there, and if we are applying a lot of stress on that material, the soil will eventually, contract. What does it mean of contraction? Because now the grains are basically in the loose soil, the grains are spread out, right? So if you are increasing a lot of, stress on that material, the soil grains will continue to come near to each other and the volume will get decreased. Now, the ideas of soil compaction were introduced in the previous years and are common knowledge. Okay. And garden and seaside, their soils have been tested previously, compaction materials and all that, how to compact this thing. So consider again the shear box experiment. Now there is a shear box experiment here, which is called as the direct shear box. We have seen this instrument in the bachelor engineering when you are doing, and probably in the module or the subject of soil mechanics, you tend to do some test on the direct shear box test. Okay. This is the direct shear box. Now, these are the two halves of the soil samples. When you are applying the normal stress and the shear stress, it fails in this way. By measuring the vertical moment of the cap, it can be determined whether the soil dilates or contracts. Now, this is the cap. Okay. Now, when you are applying the shear stress and the normal stress, the how much this thing moves actually determines the the criteria, or you can say the phenomena of soil dilation, that how much it dilates, and whether it dilates or contracts. We can measure it by, just measuring these two things. Okay. And if we look at the graphs, now these are basically the graphs that have been taken out by doing the testing in the laboratory. Okay. Now shear stress, and this is basically strain. By measuring the vertical mount of the cap, you determine whether the soil dilates or contracts. Considering typical results, but now if there is a constant effective stress, right? If we are applying a constant effective stress from out, now if this is the effective stress, this means that it is drain test. So what happens over here is that shear stress against the shear strain, and if you talk about the dense soil, it will go up, which the behavior we have already seen. It will go basically up, reaches the peak, and then it starts disintegrating. This we have already seen. So if it goes up here, it starts to disintegrate. Now, if we plot the same thing on the volume and strain graph, okay, if we talk about the volume change into strain graph, now what you can see over here, that dense soils tend to undergo dilation, because this is basically dilating after moving. Now, after moving here, it reaches peak and then it starts disintegrating and starts to increase its volume. The above section basically means that it is being dilated, the size is being increased. Okay. If you talk about the loose soil is going down here, but here you can say that it is going the phenomena of contraction, because the loose soil, if you talk about the loose soil is what it means, that if you are applying a lot of stress over the loose soil, it starts to go the over the phenomena of the contraction. Contraction basically means that it's reducing in the size. Then medium, density soils tend to undergo states in between these two things. Now the question arises here, that why does it goes a little bit of contraction and it goes an expansion? If you see over here, the graph basically touches this line and then goes up. The reason behind is that dense soils undergo slack, and dense soils basically are not actually completely dense. There are some particles which obviously are not, contracted. So therefore, when stress is being applied, what happens is it undergo some kind of slack. It expands a bit, it contracts a bit, and then it starts to go towards the change in the volume. So this there is basically a phenomena of slacking initially, but that's very minute and it happens at the start stage of this thing. But later on, it obviously uh, you know uh, starts to expand because now after yield strength, after breaking, it actually starts to expand. Now, if we talk about uh, typical results from a series of shear box tests on a sample of sand of different initial densities, this is you can see that pardon, volume change depends on initial density because how much your soil has the initial density, that too basically uh, it plays a critical role on the initial density. The soil at medium density starts to contract and then dilates. Here you can see this one. I was talking about this thing because it starts to first it starts to basically contract and then it starts to dilate. Okay, because the phenomena you can see it undergoes slack. The point at which the shear maximum is reached corresponds to the point of inflection of the change in volume, x or delta v graph. Now this is basically the maximum stage this is the maximum stage, and point at which the shear maximum obviously is reached corresponds to now, inflection. Basically delta v and delta x, these are different graphs that we will see in the next few slides. We will to know, because now there isn't any mention of these graphs here in this chapter. If we go towards the next few chapters, we'll get to know the these things. At the critical state, deformation takes place at constant value because critical state is basically the point at which obviously soil starts disintegrating. Therefore, at the critical stage, what really happens as the deformation starts to take place and at the constant volume. Thus, work is done against the normal force. So, therefore, when deformation is taking place, therefore, it's going against the normal force. Instead of plotting these data in terms of volume change, a soil parameter such as voids ratio, this is a term which we have also studied in the bachelor engineering, or specific volume, this we have also studied, could be used. The dry density of the sample is given by now. See, density basically mass per unit volume. Dry density means the soil sample is dry. Mass of solids divided by volume of solids, and this is the specific gravity times the density of water divided by 1 plus E, which is the void ratio, which is the formula of dry density. Basic formula, if we talk about the soil mechanics module, this is the basic formula of this one. So if we talk about the void ratio, we can just cross multiply and we can get an equation like this. And we know that void ratio times 1 is equal to the porosity. This is, I guess, corresponds to the specific, wait a minute. Mm, okay, so let me check. Uh, Sorry, this is the specific volume, and it relates that volume containing unit volume. Okay, so I was kind of confused. This is basically specific volume. It's not the porosity. Porosity is being shown by this sign, right? We'll go forward now. This is the specific volume, which is equal to 1 plus E. If we substitute everything values, we can get ESR is equal to the unit weight times the GS. This is another thing. This is basically the saturation of the soil. If it is equal to 1, the soil is fully saturated. This means that it has a lot of water in it. The initial dry density can be calculated from experimental measurements. What does it mean? That the dry density that is in that soil is calculated from the experimental measurements when we are doing it in laboratory. Hence, E naught and V naught can be calculated. Now, E naught basically the void ratio in specific volume can be calculated. As the test progresses, the soil experiences a change in volume, delta V, which is measured, and thus a new dry density, rho D, is calculated, and a new void ratio is calculated. Okay. So this what it means that if we are testing the soil basically undergoes change in volume. We already know delta V, which is the change in volume, which we can measure from that. Hence, a new dry density, which is rho D, can be calculated, and a new void ratio E is also calculated. So this is basically the graph between the void ratio and the void ratio and the strain for a constant, normal stress, effective stress. As you can see, this is the critical value of the void ratio. And if you talk about the loose soil, if there is a constant stress, it basically starts to contract and reaches a critical void ratio value. And if we talk about the uh, you know dense soil, it undergoes the contraction. Now loose sorry dense soil goes towards the dilation, and loose soil goes towards the contraction, which have been shown here. From figure 8, the above figure that we just studied, we can say that uh, for loose soil has a high E naught, which reduces. What does it mean? That if there is a loose soil means a lot of void ratios. So if we are applying a constant stress over that soil, it continues to reduce its volume. Therefore, the voids will get reduced a lot. If we talk about the dense soil, uh, if we are applying the constant shear stress over that, it starts to dilate. This we have already seen previously in the previous examples. At the ultimate or critical state, each sample shears under constant volume. Now, basically, ultimate state we have already studied, at which the soil starts to disintegrate, or critical state we can also say. Each sample shears under constant volume, yes, we know, at the same value of the voids ratio, which is called as the critical void ratio. Now, at the ultimate stage, when every sample, loose, dense, and medium, when it shears under constant volume, okay, at the same void ratio, then it is known as the critical void ratio. Because if at the constant volume it starts to shear at the ultimate, then it is known as the critical void ratio. We have also studied about the critical stress also, because at that point it starts to disintegrate. It should be noted that the critical void ratio is a constant for a soil sheared at particular effective stress and is irrespective of initial density. Critical void ratio doesn't depend on the initial density, but critical void ratio does change, do changes with the shear effective shear stress. This is what the concept is, regarding this thing. Now, presentation of data in the shear uh, effective stress and void ratio space. Now, these are the important graphs if you are studying the critical soil mechanics module in the University of Birmingham. You have to actually know about these graphs, because without these graphs, you cannot, uh, you know, appear like you cannot do any uh, example questions or any tutorial questions, because these are the test results from uh, the soil samples and if there is a statement given to you to solve the questions, then you have to actually know about these things. So now, shear stress, effective stress, and void ratio, there is a way to present these in a graphical format, right? Now, this graph shows shear stress versus effective stress, and a line in between shows the critical state line. Critical state line, basically, I will tell you what it is in the next view, this one. And the angle it gets is the critical inclination, or you can say critical angle. And this is for loose soil, I think so. Yes. A representation of a dense and loose soil sample of behavior is shown in the figure. What does it represent? If soil is undergoing a stress, if it is a loose soil, what it does is the shear will go up, reaches the critical state line, overtakes it, and comes back. This property is for the dense soil. But for the loose soil, it will go up and reaches the critical state line. That's it. Dense soil, why? Because dense soil, it actually goes to the ultimate and it goes to the critical state line. Because I have already explained that dense soil undergoes change when it reaches the critical state, not the critical state, but actually the ultimate state. Ultimate state, it starts decreasing and then it comes back to the critical state line. Void ratio versus shear stress. Another graph, critical state line. If we see what I want to represent over here is that the shear versus the you can say effective stress graph has been shown in the first one. But if you are plotting the same critical state line between the void ratio and effective stress, you will get a curve like this. Okay, and in this curve you can see the loose soil. If you are applying a lot of stress over this, it will eventually reach the critical state line from above, and dense it will reach from below. And this is the zone of dilation, because obviously dense soils will dilate, as I have already explained in the previous concept, and loose soils will eventually contract. And this is basically ln p dash, you can say ln or logarithmic of the effective stress. Basically, if you use a logarithmic thing, it eventually straightens the line and you will get a graph like this. Now, these are basically pretty easy graphs. You don't have to worry about, because with practice you will eventually learn this. But initially it will feel slightly hard. But if you are good at the concepts of this thing, eventually it will be very easy for you. A representation of dense and loose sample of sand behavior. Now this is basically sand. Okay, so it has explained this thing again. The two left-hand graphs in figure 9 represents projections. Okay, void ratio is equal to 0 and shear is equal to 0 respectively. Okay, this one, right? Of a three-dimensional plot in shear, effective stress, and void ratio. These basically are 2D, but actually these are 3D, which we will study in the section E or F of this module, because there you can see the graphical representation in the 3D projections. Critical state line, which is a straight line through the origin in shear, effective stress space, and characterized by critical angle, appears as a curve in void E, effective stress dash. Okay, if the data are plotted in E, LNP dash, so this is what I have explained previously, because obviously if you taking a logarithmic graph, logarithmic of a thing, it eventually straightens it. Consider the results of drained shear box test on loose and dense sample of a granular material. Granular means it's like grain type, such as sand, like in which the grains are away from each other. It's not clay, but sand. Initially, the samples are subjected to the same effective stress dash, with loose sample having a greater void ratio. Now, see, initially when they are subjected to the same dense sand, dense you can say, sorry, when they are subjected to the effective stress, okay, We know that loose soil samples will have a lot of void ratio because there are a lot of gaps than the dense sample. As one half of the shear box is forced to move relative to the other half. Now, obviously, the shear box stress is if it goes like this, the shear strength steadily increases. That we already know the strain, it will obviously strain. Since the total stress remains constant and no pore water pressure, the effective stress is constant. This we have already studied before because the rain test, there is no pore water pressure. Therefore, the effective stress will be equal to the total stress. In the case of loose sample, same. The shear stress increases until it reaches the maximum value of ultimate. Now, shear stress will keep on increasing till it reaches the breaking point at the critical state. As the sample shears, it contracts until it reaches the critical state. Now, if basically the sample shears, it will contract until it reaches the critical state at the void ratio EC, which is called as the critical void ratio. Thereafter, the soil continues to shear without any change in shear and effective stress and void ratio as the strain is increased further. Because the critical state line is the ultimate line, means it will reaches its ultimate peak capacity. After that, there won't be any change in the shear. Okay, because there is a certain point that after that nothing happens. In case of the dense sample, if we talk about the dense sample, shear increases. Yes, we know, until a peak is reached at shear maximum. This we also know because we have seen the graph before. Therefore, T reduces until constant value is reached at ultimate. This means the shear reduces until a constant value is reached at shear ultimate. Shear ultimate is same for both samples. As the dense sample shears, it dilates under a constant because we have studied that dense sample dilates when it is being subjected to the shear box test, and void ratio will start increasing, which is common to both samples. From the void ratio times the effective stress graph, we know that the boundary between loose and dense soil is definitely delineated by critical state line. Critical state line basically is a barrier, or you can say a differential between the loose soil and also the dense soil. Okay, and it also shows the zones of contraction and it also shows the zones of dilation because on the left side of the critical state line you can see that the soil undergoes the dilation because dilation means that it is increasing in size, and on the right side of the critical state line it will go to the contraction. Those soils that will contract, now the soils which are being reduced, size is being reduced, will contract under okay, sorry, I'm sorry, I'm really sorry. The soils that will contract include loose soils and normally contracted, or the NC soils are basically I forgot the term. NC basically